and welcome to Inside Ophthalmology. I am Dr. Amrit and I welcome you to another lecture. Today we are discussing the diagnosis and classification of keratoconus with a specific focus on some of the more complex topics like topographic diagnosis and keratoconus indices. In this video, we shall focus on the keratoconus indices of pentacam along with other diagnostic features. While clinical features can aid certainly in the diagnosis of keratoconus, signs like the Munson sign and Rizzuti signs are typically not seen in mild keratoconus. Other slit lamp signs include stromal thinning, Fleischer's ring, Vogt striae, and prominent corneal nerves, all of which we discussed in our previous lecture on keratoconus signs and symptoms. Additional suspicious features which can be seen clinically include high degrees of astigmatism, reduced contrast sensitivity, family history of keratoconus, also refractive instability, that is increasing cylinder or axis notation, and higher prevalence in case of Asian and Indian ethnicities. In fact, when such patients are tested with a manual keratometer, you will often observe distorted or irregular Myers, making it difficult to get reliable readings. Now, let's talk about the core of this lecture, that is the topography and tomography in keratoconus. We already have 3 videos in our course dedicated to topography and tomography, where we discuss the basics of corneal topography, the 4 primary maps, and how to read a tomography report. You'll find links to all of these in the description box. In this video, we'll be discussing many overlapping points from our 3rd video, how to read tomography. So I highly recommend you to watch that first if you haven't already. Let's now explore the evolution of topographic indices in the keratoconus diagnosis. In 1984, the journey began with the invention of the computerized video keratoscope, which allowed for objective anterior surface mapping. At that time, diagnosis was based purely on the anterior corneal surface using indices such as the inferior superior value and the simulated keratometry, that is SIMK. We have talked about that in our previous videos. Later on, the Placido-based devices were introduced, although they still analyze the anterior surface, but the major upgrade here was the introduction of composite indices calculating multiple parameters to improve sensitivity. 2 key tools emerged over here. One was the Kisa percentage index and the second was the Rabinowitz-McDonald criteria. We'll be discussing both in detail shortly. At this stage, remember that all these diagnostic parameters were still based on the anterior curvature map or the sagittal curvature maps. The next leap came with the introduction of the slit scanning and the Scheimpflug tomographers like the OpScan, which were the first to measure the posterior corneal surface, elevation maps, and the Pachimetric data. We shall be talking about the Pachimetric progression indices in our advanced video. Then, around 2010, more advanced Scheimpflug devices entered the scene like the Pentacam and the Galilei, bringing with them multimodal indices which now combine not just the anterior surface information but anterior and posterior elevation information, pachymetry, and also the biomechanical data. These indices are considered much more accurate, particularly in the early and subclinical keratoconus. So over time, we have moved from focusing on just the anterior surface to posterior elevation data, pachymetric analysis, and now even the Erometry and biomechanics. And even a new emerging technique has now developed, and that is the epithelial mapping using the anterior segment OCT. We'll try to do justice to each of these diagnostic tools, so I encourage you to watch this lecture in your leisure time with a pen and a notebook handy to take notes. Let's now understand the diagnostic flow using the 4 main topography maps. We have the axial or sagittal curvature map, the anterior elevation map, the posterior elevation map, and the pachymetric or the thickness map. Starting with the axial map or the curvature map, here we observe the symmetry or the asymmetry in the color pattern. The symmetrical shapes could be round, could be oval, or they could be symmetrical in the form of a bow tie. Here, you have to correlate it with the Kmax value. Symmetrical shapes are normal as long as the Kmax is less than 47 diopters. If the Kmax is 47 to 50 diopters, it indicates a moderate risk of ectasia. It may be keratoconus or may not be keratoconus, and a Kmax of more than 50 diopters has a high risk of ectasia. Then we look on to the asymmetrical shapes. Asymmetrical shapes definitely are suspicious. These include inferior steepening or superior steepening, and in keratoconus usually the inferior steepening is more than the superior, and therefore inferior superior difference of more than 1.5 diopters is considered suspicious. So pay attention to asymmetrical bow ties, inferior steepening and superior steepening. And then there is skewed radial axis. Skewed radial axis, abbreviated as the SRAX, is calculated from 180 degrees minus the angle between two steep axes, one above and one below the horizontal meridian. In this example, as you can see, the two steep axes form 120 degree angle, and therefore the skewed radial axis is 180 degree minus 120, that is 60 degrees. A skewed radial axis of more than 22 degrees is highly suspicious of keratoconus or other corneal ectasias. Again, these were discussed in detail in our course on topography. Irregular shapes on the axial maps are always worrisome. You might find irregular shape in other forms of ectasias like the butterfly shape or the crab claw shape in case of pellucid marginal degeneration. Irregular astigmatism or a non-orthogonal bow tie pattern suggests a very high risk of keratoconus and specifically established keratoconus. Since we are talking about the anterior surface changes in keratoconus and the role of topography, it would be worthwhile to mention the Rabinowitz classification of keratoconus. Rabinowitz classified keratoconus into four main types: clinical keratoconus, early keratoconus, form thrust keratoconus, and keratoconus suspect. Let's understand these one by one. Although this is an outdated classification or an old classification, still it's applicable because it's commonly asked in examinations. First of all is the clinical keratoconus. This is a fully declared form of disease. You will spot classic slit lamp signs like stromal thinning, conical protrusion, and Vogt striae. Topographically, you will see the classic asymmetrical bow tie pattern with skewed radial axis. Now, you might not always see this pattern. Sometimes you might find other patterns of keratoconus as well. However, Rabinowitz basically used and chose this asymmetrical bow tie pattern with skewed radial axis as a parameter for abnormality, and therefore it's included in the classification. Next we have is the early keratoconus. Here you will not find any slit lamp signs. So slit lamp signs are absent, but the retinoscopy will reveal a scissoring reflex. The topography will still show the classic asymmetrical bow tie with a skewed axis. So this is a sweet spot for early diagnosis before the vision worsens. Then we have the form thrust keratoconus, also known as the topographic keratoconus. Here, we do not find any slit lamp signs, nor do we find any scissoring reflex on retinoscopy. However, topography will quietly whisper the truth, and it shows an asymmetrical bow tie with skewed radial axis, which is a hallmark according to Rabinowitz. In today's scenario, we might also find corresponding abnormalities in the posterior elevation, Pachimetric maps, even though the eye may seem clinically silent. Essentially, this is topographically loud but clinically quiet eye. That is the form thrust keratoconus. Next, we have what is known as a keratoconus suspect. Here, the topography may show inferior steepening and mild central asymmetry. However, these do not fulfill the classic pattern criteria for definitive keratoconus. That means there is no asymmetrical bow tie with skewed radial axis. It's more of a clinical hunch because the slit lamp findings might be absent or minimal, and the retinoscopy also might be normal or unclear. The patient might progress or might not progress. Importantly, not all keratoconus suspects will develop the disease, so this term should not be equated with subclinical keratoconus. Moving on, we have the Rabinowitz-McDonnell diagnostic criteria. Now, later on in the present era, we have composite indices and stricter criteria for the diagnosis of the keratoconus. But before that, Rabinowitz and McDonald proposed two essential topographic measures as diagnostic standards, and these were the central K value and the inferior superior value. The central K value more than 47.2 diopters indicates central corneal steepening, and inferior superior value of more than 1.4 diopters indicates asymmetry due to inferior steepening. Now, these were the cutoffs which were given in the original paper of Rabinowitz and McDonald. Now, if either of these values is present, it raises a red flag for keratoconus. The sensitivity of this method is 96%. That means it's very good at catching true positives. That means the patients who really have keratoconus. And the specificity is about 85%. That means it is fairly good at ruling out false positives. Next on the list is the Kisa percentage index. A more refined composite index was developed by Rabinowitz and Rashid called the Kisa percentage index. It quantitatively combines 4 topographic parameters to assess the likelihood of keratoconus. The Kisa here stands for the K stands for keratometry. It reflects the steepness of the cornea. The I here stands for inferior superior dioptric asymmetry. It reflects the inferior steepening. S stands for skewed radial axis. It indicates the misalignment of the primary or principal meridians or the principal steep meridians or the astigmatic axis. A stands for astigmatism. The formula here is K multiplied with I multiplied with S multiplied with A divided by 300. Some important additional technical notes over here to be noted are that the K value is actually based on the excess steepening beyond 47.2 diopter. So if the K is less than 47.2 diopter, the K component is replaced with 1 in the formula. Also, the A component, that is the astigmatism, is calculated using the simulated keratometry 1 minus simulated keratometry 2 value. The skewed radial axis is calculated by 180 degrees minus the angle between the steep axis above and below the horizontal meridian, as can be seen in the image. Let's see how do we interpret the Kisa percentage. Kisa percentage of more than 100% is definitely diagnostic of keratoconus. A Kisa percentage of 60 to 100% is suggestive of form frustic keratoconus, and less than 60% is typically normal. Since it combines multiple abnormalities into a single score, Kisa percentage offers both higher sensitivity and specificity, particularly when it was used in the scans like OpScans and TMS, that is the topographic modeling system. So these were the older topographers which were available to us, which were calculating the Kisa percentage, and a part of Kisa is also available in Pentacam. Now, there are many other indices which are associated with the axial curvature maps or the sagittal curvature map, but those are beyond the scope of this video. We'll discuss about them later. For now, let's focus on the elevation-based criteria and what need to be assessed on the anterior and posterior elevation map. So, how can elevation data be used in keratoconus detection? This brings us to something very important, using both standard and enhanced reference surfaces. If you would like a deep dive into what exactly is meant by the best fit sphere and enhanced best fit sphere, check out the third video in our keratometric course. Here we explain the enhanced best fit sphere is generated. First of all, the best fit sphere takes into account all the points on the cornea in the 8 mm zone. But in case of an enhanced best fit sphere, the algorithm excludes a central 3.5 to 4 mm zone around the thinnest point, an area likely to show ectasia. As you can see in the image, the standard best fit sphere includes the values from the ectatic zone as well, making the elevation difference appear less significant. But the enhanced best fit sphere excludes the cone, which makes it more prominent and visible. So in simpler terms, the enhanced best fit sphere prevents the cone from biasing the reference surface, and this makes it easier for us to detect the early keratoconus. So let's try to understand this difference map. Now in this image, you can see the anterior and posterior elevation data relative to the standard best fit sphere calculated over a fixed 8 millimeter optical zone. Just below that, you see an enhanced elevation map, that is elevation relative to the enhanced best fit sphere. When you subtract one from the other, you get the difference map, which is color coded. Less than 5 micrometers is green and indicates that there is no ectasia. 6 to 7 micrometers is yellow, and that is suspicious of keratoconus. 7 to 9 micrometers will give you a red color coding, and that is the danger zone. Moving on, the next point is the elevation at the thinnest points. Another critical value is the elevation at the thinnest corneal points. These values will differ for myopes and hyperopes, and the standard deviation cutoffs will vary. For myopes, what you can remember is the anterior cutoff is 8 micrometers and the posterior elevation cutoff of the thinnest point is 18 micrometers. For hyperopes, the anterior elevation of the thinnest point cutoff is 7 micrometers. What I mean to say is the thinnest point elevation on the anterior surface for a hyperope should not exceed more than 7 micrometers, and the posterior elevation point of that thinnest point should not exceed more than 28 micrometer. You would notice that the myopic eyes can tolerate more anterior surface irregularities, whereas the hyperopic eyes show higher posterior elevation thresholds. Next, we have the Pachimetric maps. So we finished the anterior sagittal maps, we finished the elevation data, and we covered some of the indices in both these sections. Next, we'll talk about the Pachimetric maps. We can also use the thickness map or the Pachimetric map to detect the keratoconus by evaluating that thinnest point displacement. So first is you locate the thinnest point, you calculate the displacement of the thinnest point along the y coordinate or the y axis. If the displacement is more than 0.5 millimeters inferiorly or 500 microns, that is suspicious. Also, what we can do is we can find symmetrical locations in the upper meridian and in the lower meridian, and we can calculate the difference in their thickness. If the inferior superior asymmetry is more than 30 micrometers, that is also risky. So this summary here helps. Y coordinate displacement from minus 0.5 to minus 1 with the thinnest thickness of 470 to 500 micrometers indicates moderate risk. Thickness of less than 470 microns and displacement of more than minus 1 millimeter indicates high risk. Minus indicates that the displacement is in the inferior direction, which is typical in keratoconus. Alright, now let's talk about the Pachimetric analysis in the Bellin Ambrósio or the Ambrósio's display. I really want to apologize for my pronunciation, and if any one of you is finding it difficult to follow through, you can switch on the subtitles. Earlier we discussed how elevation data is analyzed in the Bellin Ambrósio display. Now let's look at the Pachimetric analysis section. Now this is an advanced section that you see on the pentacam. You will find two parameters adjacent to the exclusion map. These are the CTSP and the PTI. CTSP stands for corneal thickness spatial profile and PTI stands for percentage thickness increase. First, let us discuss the corneal thickness spatial profile. This evaluates the thickness of the cornea along 22 concentric rings, each increasing by 0.4 millimeters in diameter, centered on the thinnest part of the cornea. On the graph, the red line represents the patient's corneal thickness progression, while the central line shows the average progression in the normal population. This is flanked by the dotted black lines, and they basically signify the 95% confidence interval. The next parameter is the PTI. The PTI, the percentage thickness increase, measures the relative increase in the thickness as a percentage compared to the thinnest point. So it focuses on how quickly the cornea thickens outward. We all know that the cornea is thinner in the center and thicker in the periphery, and that is what is known as the thickness profile. Now we are testing it using these two parameters. In case of PTI, we are doing it in terms of a percentage instead of absolute microns, what we did in CTSP. In simple terms, the PTI is going to tell you how much thicker the cornea gets in percent as you move away from the thinnest location. You can see the PTI formula here, that is the thickness at a given ring minus the thinnest thickness divided by the thinnest thickness into 100. The red line, if the red line dips below the dotted line within a 6 mm zone, it suggests rapid thickening, that is high risk of keratoconus, both in case of CTSP and PTI profiles on the Bellin Ambrósio display. Next, moving on, we have an advanced index called as the BAD D score. So we all know what a BAD display is. BAD is nothing but it is Bellin Ambrósio display. But BAD D has an additional D, and D here stands for Deviation Score. The Bellin Ambrósio Enhanced Display with the D reports 5 key parameters, each showing how far a measurement deviates from the normative database or from the normal data. These values are the DF, that stands for anterior elevation deviation. DB is the posterior elevation deviation. DT is how much the corneal thickness deviates from the normal database. DA is the thinnest point location deviation. And DP is the parametric progression deviation. Thank God we don't have to do all of these. The machine calculates all these parameters for us. Each parameter is color coded and expressed in terms of standard deviation. The final D value is calculated by regression analysis, comparing your case to a population of normal and keratoconic corneas. The interpretation goes like this. If the D score is less than 1.6 standard deviation, the color is white and it indicates normal. If it is 1.6 to 2.6, the color coding is yellow and it indicates suspicious keratoconus. And a D score of more than 2.6 standard deviation gives a red color, abnormal and high risk. Sometimes one or more parameters may be abnormal, but the overall D score will remain normal. That's why it's essential to view the entire display holistically, not just isolated value. So this figure shows you exactly where to locate the D value on the pentacam display. Another valuable tool in keratoconus diagnosis is the InterEye Asymmetrical score, which compares the corneal parameters between both eyes of a patient. As we know, keratoconus is often bilateral but asymmetric, so detecting subtle differences between the eyes can help identify early or subclinical ectasia. Here's how it works. Each parameter that exceeds a predefined threshold is given a +1 point. These are the commonly used thresholds. For mean anterior keratometry difference more than 0.30 diopters, a +1 score is given. For mean posterior keratometry, the difference cutoff is more than 1 diopter. For thinnest pachymetric difference, the cutoff is 12 micrometers. And the anterior elevation at the thinnest point difference between the two eyes, the cutoff is 2 micrometers. For posterior elevation at the thinnest point, the cutoff is 2 micrometers. So I hope you are able to follow that we are basically trying to compare two eyes, and based on the cutoffs we are giving the scores. These values are all based on literature derived thresholds, though different institutions may use slightly modified versions of these criteria. How do we interpret the score? Score more than 3 is seen in 6 to 11% of the normal eyes, so you interpret this with caution. Score of more than 4 is seen in less than 4% of normal eyes, and therefore this is highly suspicious. However, if the score is equal to 5, it is seen only in 1% of the normal individuals, and this is strongly suggestive of keratoconus. So a score of more than 4 should raise red flags and prompt further investigation in these patients. Let's move on to advanced diagnostics in keratoconus, and here we have the role of anterior segment OCT in early keratoconus. A significant new modality in keratoconus detection is the epithelial thickness mapping using OCT. Here's what happens in keratoconus. The corneal stroma develops a localized protrusion or bulge, the cone. This is what we discuss in detail in what is keratoconus or how ectasia develops. The epithelium, which is the outermost layer of the cornea, responds to this by undergoing remodeling. It becomes thinner over the cone and thicker in the surrounding annular zone. This creates a characteristic epithelial donut pattern, that is thin centrally over the cone and thick in the surrounding ring. Now, why is this important? This epithelial remodeling serves to smoothen out the stromal protrusion, making the anterior surface appear deceptively normal on topography. As a result, in very early or subclinical keratoconus, the cone may not be visible on anterior surface topography because the epithelial layer is effectively masking the irregularity. So how OCT helps? By mapping the epithelial thickness, the anterior segment OCT can detect these localized epithelial thinning at the apex and compensatory thickening in the periphery. And these subtle changes may be missed on standard topography but are easily picked up on epithelial maps. As you can see in the top images here, the area of the cone appears green and yellow, which wouldn't raise much concern, but on the epithelial thickness map, you can clearly see the thinning centrally and thickening periphery, confirming epithelial compensation and also keratoconus diagnosis. Now, I would like to discuss some of the advanced diagnostic tools that we can use for diagnosis of keratoconus. Number one is corneal hysteresis. Did you know that your cornea also has a shock absorbing ability? So that's what we call as corneal hysteresis, which is a biomechanical property that reflects how well the cornea will resist or absorb external forces. We discussed about this in our video on what is corneal ectasia and how corneal ectasia develops, wherein we discuss about the biomechanical properties of the cornea. So you can visit that video by clicking on the link in the description box or the link which is appearing in the I section on the right side of your screen. In keratoconus, the cornea becomes thin, weak, and biomechanically unstable. And guess what? The corneal hysteresis is also going to drop significantly in keratoconus eyes compared to normal eyes. And therefore, even before visible topographic changes appear, you can pick up these ectatic changes by measuring the hysteresis. So how is it measured? Using some instruments like the ocular response analyzer. The graph over here displays a pressure versus time waveform created during the air puff test. As you can see in the image as well, the device creates or releases a brief air pulse that causes the cornea to deform inward concave and then return to its normal shape, that is the convex shape. As this happens, at 2 points applanation occurs or the flattening of the cornea occurs. The first applanation, that is the P1 point, is when the cornea flattens while being pushed in, and the second applanation P2 is where it flattens again as it comes back out. You will see two distinct peaks. The first peak P1 represents the inward pressure needed to applanate the cornea, and the second peak P2 represents the outward pressure during the recovery. The difference between these two pressures is known as the corneal hysteresis, which is P1 minus P2. The narrower is the gap between the peaks, the lower is the hysteresis, and more biomechanically weak the cornea is. In normal corneas, the P1 is higher than P2, and corneal hysteresis is usually more than 10 millimeters of mercury. Whereas in keratoconus, the cornea is more deformable and it gives in more easily. Therefore, P1 and P2 are closer together. The corneal hysteresis drops to less than 9 millimeters of mercury and even less than 8 millimeters of mercury in advanced cases of keratoconus. Another advanced diagnostic tool is the Erometry. The Erometry measures the way light travels through the eye. It detects optical imperfections that traditional refraction or topography might miss. In keratoconus, the irregular corneal shape creates not just a blurred vision but also complex high-order aberrations. These are the coma, which is the most characteristic high-order aberration in keratoconus, trefoil, which is another frequent irregularity, and spherical aberration, which is less common but present in advanced cases. Coma looks like a comet tail on the wavefront map, and it correlates with the inferotemporal steepening typical in keratoconus. Now, why is it important? Because Erometry can detect early keratoconus even before topography shows changes, and it helps explain poor visual quality in patients with relatively good visual acuity. Thank you so much for watching. We hope this video helped you understand the diagnostic approach to keratoconus better and that we could do some justice to this important topic. If you found value in this content, don't forget to subscribe to the channel if you haven't already, and do share it with your friends and colleagues. We are on the journey to reach 1 lakh subscribers and your support means the world to us. For those of you who are interested in more advanced content, including detailed indices from devices like Sirius, Galilei, and in-depth additional pentagram parameters, these would be covered in our membership section as they may be more relevant to a niche audience. You can find the membership link at the end of the description box below. Thanks again for being here. Take care and have a great day.